Next up, we didn't plan that actually, but it's a great way to sort of introduce your talk, Mo. Is Mo, who came all the way from Toronto,
Montreal.
same thing, all the way from Canada, to talk about how not to run Redis, which is kind of the talk I love most. It's lessons learned in production, I guess, or
Yep.
hard battle stories that you're going to tell us, and in sharp contrast to what Hekel just said. So, Mo, thank you.
Hey, thanks for having me. As I was introduced, my name is Mo. I work for Shopify in Montreal, Canada. I actually pulled the rug under the feet of a few people. I slightly changed the title of my talk. I removed the "not," so sorry about that. Given it's my first talk at this sort of event, I decided it's maybe more cautious for me to talk about how to rather how not to. So Shopify is an e-commerce platform. So who here shops online? Who here shops online not on Amazon, Alibaba, or eBay? So you probably shop on Shopify, or at least on websites powered by Shopify. Simply put, we help businesses from grannies selling candles from their homes to Kanye West and the Kardashians. We help all sorts of businesses. And in the Ruby on Rails community, we're known for being one of the largest and oldest Rails applications in the world. Some numbers to give you an idea of the scale we run at. My team focuses on background job processing, so this is the number that's the most relevant to me and the one I will focus the most on. We run about 1.6 billion background jobs per day. This is all powered by a library in Ruby called Rescue. I'm sure a few of you will know it if you're Rails developers. And it's backed by Redis as a queue. So today I will just outline a few use cases that we have about Redis. I will mainly talk about two things, so give you an architecture overview. So maybe this is a bit of like the how to or how not to. I will touch on a few topics about how we run Redis and Rescue at such a large scale. And also we'll talk about some of the resiliency concerns we have and how we deal with them in Redis and why they're important. So at Shopify, we run a lot of Redis instances. So most of them are what we call ephemeral. So these are non-persisted sort of data stores for various use cases. So this is where we store our user sessions, our shopping carts, and we have a bunch of disposable instances that we let the developers connect to for whatever features they might need. The most critical one is our persisted Redis instances. These are the ones that power Rescue. So this is where Rescue will hook into to basically in-queue background jobs to be processed at a later point in time. If we look at Shopify and sort of how it evolved, it kind of started as a simple web application. We use MySQL as our primary data store. So this is where your business information is going to be, where we have your products, your checkouts, everything, all the data we need. And we have our Redises. So at first, as a pretty small application, we have one instance of MySQL, one of Redis, and then we have workers, right? We mainly have two types of workers. These are Rails applications or instances of a Rails application. Web workers are going to process web requests, right? They come in through the load balancer, and then they get some kind of logic that they need to run, talk to MySQL, Redis, get the work done. And job workers are basically rescue workers, which talk mostly to Redis to get work, and then in the same fashion, they have their own logic to get work done. Anyone familiar with these? So these are collector sneakers, off-white blazer mids. Funnily enough, they're a big reason, like collector sneakers affected our architecture a lot. So we have these things called flash sales. So a flash sale is when some sort of really rare item or like some limited edition item drops in very limited quantities. And then what happens is that we see crazy spikes of traffic coming into our platform. So at any point in time, even maybe during this talk, we're one tweet away by Kanye West, hey, I dropped my Yeezys, or some other rant by Kanye, away from getting huge surges of traffic to our application. What does that mean? So that means a lot of writes. So when a checkout happens, it's a lot of bookkeeping, right? So we need to keep track of update inventory state. We need to enqueue a lot of background jobs to be performed at a later point in time to save on performance, because not everything can happen within the request itself. And what this means, essentially, is that sharding for us wasn't really an option, except the only option. There's only so much caching you can do, right? So at the end of the day, you can't cache a write. If you're bound by the number of writes you can do, you can purchase a bigger machine, a bigger like MySQL server, but that will only get you so far. So in the challenges of scaling a very write-heavy application system, this was the first step. This was fine at first, so Redis was able to keep up, right? Where the web workers are still enqueuing a lot of jobs. The job workers might do the same, and everything is fine. But it's only a matter of time before we hit the same problems with the Redis instances. And as we scale also, and if we only scale the MySQL instances, the pressure on that one Redis as a single point of failure becomes increasingly dangerous for us to rely on. So enter the concept of a Shopify pod. A Shopify pod is basically a generalization of a MySQL shard. So we piggyback on the concept of a MySQL shard, which is going to store a subset of shops, right? So each shop, when signing up for Shopify, will get assigned to a shard. But now we piggyback on this concept and put in a lot of the resources that need to be to scale with the number of writes. So Redis being one of them. So when our clusters grow, the way we are able to scale is by spawning up more pods and routing signups to them. So if these three pods are going to fill up, we can spawn a pod D with, at first, which will be empty, both in MySQL and Redis, and we're able to route signups to there, and that will organically grow. A very important thing for us, even because of flash sales, is capacity elasticity. So why are web and job workers not podded? Because the potential for one shop to generate huge amounts of traffic is non-uniform, right? So some shops are very tiny. They get us like a tiny bit, like a tiny rate of requests. But like as I said, at any point in time, off-white sneaker might just drop on the market, and then pod A will require all of our resources. And that's why we basically share pools of workers across all pods. These things run in multiple data centers for redundancy. So at any point in time, a pod is only active in one data center and passive in at least one or many data centers. And the reason for that is redundancy. I'll get into more detail. I'll talk about failovers with more detail later on. But the key thing to keep in mind for now is that we run in multiple data centers. Web workers, what do these look like? So web workers get process requests synchronously, right? So the load balancer will route a request to web worker, and that request will have, of course, a URL, HTTP verb, and all those things. But more importantly, our web workers recognize which Redis and pod to connect to at the application layer. So The load balancer is responsible for for relaying that data to the web worker. And in this instance, for example, the request is tagged with pod A. So that's how we know that that web worker for this request to process this checkout in this case needs to talk to the Redis in pod A and not in pod Z, which is passive in this case, in this data center. Job workers work differently. So they run rescues logic. And the way we run them in our case, because rescue only assumes one instance of Redis at any point in time. The way we make it work in the case of having multiple pods is that the job is constantly busy iterating over all pods in its data center, looking for jobs to process. So the one thing to keep in mind, certain pods in the data center are passive, right? So we need to skip them. So that's kind of like the life cycle of a job worker in our data center. What happens when we have a lot of these things? You can imagine per data center we might have thousands of job workers. We do and will have even more, hundreds of Redis instances. And each web worker, because we need capacity elasticity, is going to be talking to every single Redis in the data center. So you can imagine the craziness that ensues. These Redis instances are basically wasting so many CPU cycles just like maintaining connections, like tens of thousands of job workers. But it's very critical for us that these job workers are shared. So how do we conciliate the two things? So we settle for a sort of middle ground called worker groups. So worker groups is kind of like just splitting your data center in half and saying, hey, these two job workers are worker group number one. They only talk to certain Redises. And these other job workers will talk to another subset. It's not a silver bullet. It's just basically trying to perform a balancing act between having Redises that are not very busy just monitoring and maintaining connections, and also having shared capacity between Shopify pods. And these are configurable, and we can spawn as many worker groups as needed as we grow. So what else happens when you scale and have hundreds of Redis instances, workers, resources in general? One thing you start seeing is resiliency becomes a real concern. Because when you run a small application, if you have some sort of edge case that can happen only 1 in a million times, and you have, let's say, 1 million requests or 1 million workloads every month, that error will only happen every month, right? But if you see millions of those workloads every hour, every day, now that little edge case is basically like your worst nightmare. It's haunting you every day. Another thing is that if you run in the cloud, which is our case, we run on Google Cloud Platform and Kubernetes, you lose a certain level of control over your hardware. You're at the mercy of your orchestrator or your cloud platform for things like server restarts, node upgrades, nodes being taken out of rotation, and so on. So the thing that, these things become unavoidable. And one thing that Redis does that helps us mitigate these things is a very neat feature in Redis persistence. I'm sure many of you know the internals of this quite well. The way it works, this feature is very configurable. So the way we use it is essentially achieves snapshots on disk of the Redis memory around every second. This is very neat. So if a Redis pod gets preempted or restarted, we're able to boot from a snapshot that was recorded hopefully very shortly before the restart, or hopefully even have that memory snapshot be the exact same point we want to start from. However, no matter what persistence configuration you use, there's always the potential for data loss in the case of non-graceful termination. So between these snapshots, if your Redis instance gets killed in a non-graceful way, in a way that it can't basically salvage the data back on disk, there's always potential for data loss. And what that means for us, we lose jobs, right? So if you're processing a checkout and that gets lost in the middle of a non-graceful Redis termination, that means you might not get that email, you might not get that payment processed, et cetera, et cetera. So in all cases, we need to have another layer of resiliency, which we are able to achieve with this redundancy across data centers. And this is the ability to fail over. This is critical in many scenarios. So again, incident response. If something goes horribly wrong in one data center, we want to be able to evacuate to the other data center. And that includes evacuating many things, right? So we have MySQLs that we need to fail over, and then we have the Redis instances that we need to fail over as well. And I'll tell you in a second how we do this. These things are all these orchestration steps that go into a failover. We have a tool called Active Failover that handles them. And this tool is basically running in every data center. And very simply put, it has three main steps. First of all, our MySQL databases are replicated. So the MySQL in the active region is the master, and the one in the passive region is the slave. And what happens during the failover is that we basically need to swap the roles of who's the writer and who's the reader. And there's a little cutoff period there that there's some logic there to let the replication catch up, basically. In the middle, right after that, we're able to pause requests at the load balancer level. This is a very neat feature that we're able to have working in our load balancers that run Lua modules on top of Nginx. And what happens is that this is where we're going to go and tell the load balancer that the active location for pod A is going to be east and not west. So it's basically like updating an entry in a table that says active location is east, not west. And finally, we fail over Redis. This is basically us failing over pod number 21 from our Slack. We use Slack a lot for our as our CLI tool to perform opsy things like failing over. So how do we fail over Redis? I made sure to put it in quotation marks because I think it's quite unconventional and a little creative. So because this happens right after we updated the active location in the load balancer, we're now in the passive region, right? So this Redis is still up, it's running, it still has data, it still has some jobs waiting in a queue, but no requests are coming to web workers in this data center for this pod. Job workers aren't worried about this Redis anymore, they're not trying to work from it, no one is talking to it. So we're in the passive region, but yet we still have data in here that needs to go to the active region to be worked off, right? If you have an email job waiting here, it needs to be sent to the active region for it to ever show up. So how do we do that? So inside active failover, we have this tiny piece called transfer jobs. It's basically a very fancy for loop that is going to basically scan all the keys that we need to move over to the active location. Because between these two data centers, this traffic, sending data might actually go over, we don't know which network, it might be public. We use a TLS tunnel. So this is data that, basically every rpush command that's going to the active Redis needs to be through a TLS forwarder. And how do we keep track of everything going well? We basically we have a monitor that runs over these passive Redises or Redis instances. I always wondered what the plural of Redis is. I'm sure we can talk about that after. And basically this monitor is what will tell us if everything is looking good. We want the number of keys that we're looking at to go to 0 as fast as possible. So some of you may be wondering, why not use Redis replication, right? So it's a feature. You can just set your your Redis in the active region to be the master, and everything else to be the replica. There's a few reasons for that. One is the nature of the access patterns on these Redis instances. So in the case of enqueuing a job, we're performing an L push. And in a healthy system, what we expect to happen is right after that, like as soon as possible, for there to be an L pop. So as soon as there's a job enqueued, we expect a worker to pick it up. So essentially, when that happens, these are two operations that we don't really need to replicate because that job is processed. What's the point of sending it over to the passive location, right? The second thing is a bit more nuanced and like, I guess, use case specific, is that cross data center traffic is billable by Google Cloud Platform. So if I'm talking to a pod that's in another data center in Google Cloud Platform, whatever traffic I'm using, bandwidth, we're getting billed for it, right? And let's say we have a flash sale in East, and then we get a crazy spike in jobs. And we send we replicate all this to the passive region, and everything is healthy, so all these jobs are basically being worked off. Like, we're sending no ops and like burning money for no good reason. The last thing is that this puts stress on our TLS tunnels, right? So right now, we care that our TLS tunnels are up only for the duration of a failover. And in this scenario, we need them to be up at all times 24/7. So it's basically, this setup is just a tiny bit more complex than what we actually need. So we try to, and we obviously in these sort of architectures, we try to optimize for simplicity as well. That's not to say that our approach is perfect, right? So transfer jobs is still an imperfect solution, and we're always like trying to look for ways to improve it. One of them is that we're not relying on Redis or like on a feature in Redis to replicate these keys that we need. We write our own Ruby code, right? So if that's prone to bugs, essentially that means we lose data, right? If your payment processing job doesn't get failed over, if your email sending job doesn't get moved, we lose data. We might corrupt data even. So that's something we're very cautious of. Even in the cases where everything works fine but is a bit slower than we anticipate, we might miss our SLOs. So each job, depending on the criticality of it, has an associated SLO. So a payment processing job, we'd love for it to be processed as soon as possible. If you have some sort of backfill, or another less critical job, it's okay for it to be processed within the hour. But if we're doing things asynchronously, the way we're doing, we might miss those SLOs. And then there's the entire subject of race conditions between workers in the passive region and failing over. That could be a subject of its own talk. So in closing, in our case, sharding was very helpful. We're very write heavy because of flash sales. So we had to piggyback on that concept when sharding MySQLs and kind of put Redis in there as well. This really is no silver bullet solution for running multi-DC active passive architectures. A lot of trade-offs to be done, like I showed, and really understand that simplicity is key, right? So if it means writing your own custom code to make your Redis architecture work, or actually knowing when something is a very good use case to just defer to Redis. And I'll be around. Come talk to me about anything that you thought was interesting or not. We're hiring at Shopify, so also come talk to me for that. I just got a Twitter earlier today at Moshayeb. I was told that people might tweet my name and stuff, so yeah, sorry I didn't include it. But yeah, I'll be around. Thank you.
Thank you, Mo. Thank you. That's brilliant. I love to see how people like tear Redis apart and start using it in ways that they want.